So welcome everyone. So it is my pleasure to welcome today Darren Wilkinson. So Darren is a professor of statistics at Durham University in the UK. And Darren has worked on many applications of Bayesian statistics and on a variety of challenging big data problems, so in molecular biology and engineering. So in particular, he wrote a book on stochastic modeling for system biology. And he's also working on understanding the extent to which category theory and pure functional programming can provide a foundation for more scalable approaches for Bayesian modeling and computation. And so in this talk, Darren will provide us with more information about this specific topic by discussing compositional approaches for scalable Bayesian computation. So Darren, I will let the mic.
Okay, that's great. Thanks very much. Thanks for the introduction. And thank you for the introduction to speak in this series. I think of all of the webinar series that sprang up over COVID, this one's been my favorite. I've listened to most of the talks either live or later on YouTube. It's been great. So thanks very much for organizing it. All right, so hopefully you can see my screen now. So today I'm going to talk about compositional approaches to scalable Bayesian computation. Okay, so what's that all about? Well, I'm going to start off with just a little bit of background, what the issues are, what are the problems that we currently have with the current approaches, and in particular, the current programming languages we use for doing Bayesian computation and why they don't really scale very well. We'll dive into some of the details and look at how functional programming languages give us a lot of advantages and why they give us advantages, where those advantages come from, and how they're going to cash out. And we'll look at a few different languages and libraries and frameworks along the way there. But I don't want to get too bogged down in the technical details. So at some point, I'd like to just take a step back and think about what's really going on. What's the kind of mathematical structure that's underpinning the reason why some computations are better expressed in some languages than others, how it all fits together, what it's got to do not only with getting algorithms to run faster, right? So that's what a lot of us are concerned with a lot of the time, is just making things run faster. But there's more to scalability than that. There's also building big and complicated models in a compositional way, safely and meaningfully and correctly. And so how does that all fit together, and sort of where are we going? All right, so some background first of all. So we're presumably all interested in Bayesian computation one way or another, otherwise we wouldn't be here. And for non-trivial problems, which again, most of us are interested in, ultimately that's going to rely on some kind of computationally intensive method. Now, I should kind of say up front that I'm really interested in sampling. So that would be MCMC, SMC, or ABC. I understand that not everybody who does Bayesian inference does sampling. And I understand that there are computational challenges. Indeed, there are scalability challenges associated with doing sampling. But my gut feeling is that we should tackle those problems head on and deal with those scalability challenges rather than kind of do something else. So really, I'm interested in drawing samples from a posterior distribution. So fundamentally, they're going to require some kind of implementation in some kind of programming languages. And basically what I kind of claim is that essentially all of the languages that people use, or almost all of the languages that people use, are not very well suited to this. And the reasons are basically just that they're all very old language. They all date back to really the dawn of the computing age. And computers were very different then, and we didn't know as much about how to design good programming languages. So lots of people interpreted dynamic languages. They became very popular sort of in the 90s, I would say. And they seemed like a good idea at the time. I think a lot of people now think that they were a terrible idea and that we should never have gone down that road. But, you know, that's kind of how things go. So languages like R, Python, MATLAB, etc. There are lots of problems with those languages. But I think one thing that pretty much everybody agrees on is that they're far too slow for doing serious Bayesian computation. So we'll leave that there for now. But not all languages are too slow. Obviously, languages like C, C++, Java, Fortran, etc. They're all very fast languages. But I would argue that in many ways, they're even less well suited to doing scalable statistical computing than the dynamic languages, really fundamentally in terms of their language structures and features and the way they allow you to build and compose code. And in particular, in the way they allow you to take advantage of modern computing hardware. Okay, so that's kind of setting the scene. All of these languages are kind of terrible in one way or another. So why is it? Well, they're all fundamentally imperative programming languages. Okay, so that is, they say what to do and when, and that's very problematic when it comes to building scalable algorithms. Now, it's not surprising that languages arose like that. You know, they arose like that because they were mimicking quite closely the way that early computer processors worked, right? So early computer processors, work by just saying what you do and when. And so it's not very surprising that the programming languages we developed back in those early days kind of mimicked that structure to a greater or lesser extent. But just as there have been huge advances in statistics in the last 50 years or so, there have been just as many advances in computing science in the last few decades. And we know a lot more now about how to build good programming languages. And in particular, I would argue that we are kind of gradually coming to realize that there are a lot of advantages associated with functional programming. Now, actually, functional programming languages also, one way or another, go back to the dawn of the computing age, but there's been a big resurgence of interest in those languages in the last decade or two. And again, I would argue that it's largely because they have turned out to be much better at building software at scale. And so with the kind of internet revolution, etc., people have wanted to do things using modern computers at scale, and people have found that functional languages make it much easier to develop software in a modular, composable way that scales and that can take advantage of multiple processors, etc. Okay, there's a slightly orthogonal point, which is the dynamic typing point, that again, there's also been a swing away from dynamically typed languages back to statically typed languages. It's a slightly different point, but it's actually also very important. Types really do matter when it comes to building software scalably and correctly. And again, there's been very much a swing back to statically typed languages in the last decade or so. Right. So what are functional programming languages and what makes them different? I think the thing that really sets them apart is their use of immutable data and pure referentially transparent functions, and the use of higher order functions. So functions as first-class objects, okay? But it's really the kind of immutability and the pure referentially transparent functions that really makes them so useful for building scalable software in a kind of composable way. So these FP languages, they support composition of models, data, much more naturally than imperative languages, and there are lots of benefits that come from that. So when people talk about functional programming, they often start mentioning category theory and ideas from category theory like monads, and they are important, but again, they're sort of secondary to this idea of being really about immutability, pure functions, higher order functions. I think they're the really important things. I think these ideas from category theory are also super useful, but they're sort of less important than the basic notions of immutability and referential transparency. But these statically typed functional programming languages, so Haskell and Scala being kind of the probably most popular examples, in lots of ways, they correspond to quite closely to a model of computation, a mathematical model of computation called the simply typed lambda calculus. Now, the thing about that is that that's one of the canonical examples of a mathematical structure called a Cartesian closed category. So that's the connection between FP and category theory. And it turns out that because of that connection, we can borrow ideas from category theory and bring them into FP to help us solve problems. And this isn't just a theoretical exercise. They give us really kind of practical and useful ways of solving functional programming problems. And in particular, they help us to simplify code in a way that maybe it wouldn't be obvious how to solve the problem in a functional language in a neat and elegant way. And not only does it help us see how to solve the problem in a neat and elegant way, it allows us to see what the compositional structure is. So how to build things by plugging them together to make bigger things, right? So not only does it help us solve the immediate problem, but it helps us then solve the bigger problem as well. Right, so I guess the killer application of functional programming languages, and the reason they've become so popular recently, is that they really solve this whole problem with concurrency, parallelism, distribution, and state. Okay, so a modern computing platform, it will have many processors, probably. Each processor will have many cores. You might have GPUs, you might have a cluster of machines, right? You might want to exploit all of this, this computing power that you have at your disposal, but some way or another, you're going to need some kind of parallel programming in order to properly exploit that. Now, if you've ever done any parallel programming, you'll know that it has a reputation for being very difficult, okay? And with good reason, because if you try and do parallel programming using traditional imperative languages like C, with libraries like MPI, it is horrendously difficult and very difficult to debug and very difficult to get correct. So why is it so difficult? Well, when you track down why parallel programming is so difficult, nearly always all of the problems stem from some kind of problem to do with shared mutable state. Okay, so there's some state on some processor and some thread. Maybe you change it on one thread, and maybe you do that at the same time as some other thread is trying to change it or access it, and that causes problem. Or maybe it's on a different processor, and the other processor doesn't know you've changed the value, so you need to synchronize it and transfer it off across to the other processor, etc. So all of these problems ultimately boil down to problems with dealing with shared mutable state in a correct way. And that turns out to be very, very difficult to do. But in these functional programming languages, I've just said we emphasize immutability, okay? So generally state isn't mutable in functional programming languages, right? So there is no mutable state, shared or otherwise. And so a lot of the problems associated with parallel programming just don't exist in functional programming languages. The way we express our programs, it's clear what can be done in parallel, what can't, what the synchronization points are, etc. And this can all be automatically analyzed and dealt with programmatically without any user intervention. And so it becomes then very easy to write scalable, correct parallel programs. And it's this kind of natural scalability that I think has led to the recent resurgence in FP languages. Okay. So that's kind of the killer feature of functional programming languages, and it's the thing that lots of people talk about. But in some ways, that's not really the be all and end all. I think that the parallelism is really one consequence of functional programming languages being more modular, composable, and scalable, right? And so that manifests itself in many ways, and one way it manifests itself is in terms of it making it very easy to do parallel computing. But that's just one way it manifests itself. But fundamentally, it's just a more scalable way of doing things. Okay, so we know, right, that the way we tackle big, complicated problems is we break them down into smaller problems, we solve the smaller problems, and we assemble them back together, right? We do this all the time. We do it in life, we do it in mathematics, we do it in computing. This kind of divide and conquer type approach we use all over for all kinds of reasons. And again, one benefit of doing that is parallelism, right? So if you can divide a problem into pieces and the pieces can be solved independently, then they can be done in parallel. But even when they can't be done in parallel, or even if you don't want to do them in parallel, there's still often huge benefits in terms of doing this kind of divide and conquer approach, either in terms of correctly understanding and decomposing the problem to get a correct solution, or in terms of benefits of scalability, computational cost, right? So famous things like the fast Fourier transform, right? Even if you're doing this on one processor, right, you're not doing it in parallel. By noticing that you can do a discrete Fourier transform by doing discrete Fourier transforms of the odd and even elements separately, right, you immediately get the kind of tree reduction, natural tree reduction strategy. And so, your order n squared goes to order n log n, even on a single processor, right? So, if you can parallelize two, then that's great. But even if you can't, that happens. And it's same with belief propagation on probabilistic graphical models. In principle, the complexity is exponential in your number of nodes. It's just completely hopeless. But if you use the conditional independence structure of your probabilistic graphical model and decompose according to that conditional independence structure, then you get massively reduced complexity, in best case sort of linear in the number of nodes, right? So this divide and conquer is a natural thing to want to do. And it's very easy and natural to do that in these functional languages. It's the natural way to solve problems. And it's not that you can't solve problems like that in imperative languages. You can break them down into pieces. The problem comes when you're trying to assemble them back together again. In an imperative language, if you're not dealing with pure functions, once you start assembling things back together, all kinds of things can go wrong that don't go wrong when you're working with pure functions. Okay, and the connection to category theory again is that category theory is basically the mathematical study of associative composition, right? And so that's again where the connection comes from. Okay, so what are the kinds of things I want to talk about? Well, when we're doing Bayesian computation, what kinds of things do we like to do? Well, we like to do likelihood evaluations for big data sets. Well, that's quite a naturally parallel thing, right? So it's kind of clear that if you've got IID case at least, you can parallelize your likelihood evaluations across your observations. Similarly for ABC algorithms, right? You can often propagate particles in parallel, right? So that's quite a natural parallel structure. And similarly for sequential Monte Carlo, you can often do your propagation, reweighting, and resampling in parallel to a greater extent. The resampling is sometimes tricky, but even that you can kind of do in parallel to some extent. So those kinds of problems, right? The parallelism is obvious and natural, and so that's fine. And we'll look at what the model for that is. It's basically just a functor. But other algorithms, it's maybe not so obvious. So for example, Gibbs sampling on a big graph, say an Ising model or a Gauss-Markov random field, doing a Gibbs sampler for that, is it obvious how to express that in a pure functional way? Well, it's less obvious, but it turns out that this is one of those cases where ideas from category theory come in handy. So it turns out that if you've got a pointed data type, then the comonadic interpretation of that pointed data type gives you a natural way to essentially propagate local computations to global computations. Yeah, so in a Gibbs sampler, you're doing local computations, right? At each node, you're sampling the node from its neighborhood. That's a local computation, and you want to apply that all over your graph. Okay, so that's extending that local computation to a global computation, right? Well, that's just a co-bind operation on a comonadic structure. And similarly for any kind of convolution operation, right? If you're doing convolutional neural networks, right? This comonadic structure is exactly what you need to express these cleanly in a functional way. Similarly, probabilistic programming languages, we'll come back to this later, hopefully. It turns out that monads are the right way to build and compose probabilistic programs. Again, in a modular, scalable way where pieces can be glued together to make bigger models in a way that's not easy to do in existing probabilistic programming languages. And again, a bit orthogonal to this talk, but automatic differentiation is the same story. It's very natural and convenient in functional languages to be able to auto-diff those pure functions. Again, it's all about the purity of the functions and not having side effects. They're not being mutation. It makes it much easier to analyze an auto-diff through your computation. So getting a little bit specific then, a functor is just something that you can map, okay? So if we've got this example here, we've got a vector and we map it with a doubling operation, we get a new vector. It's absolutely clear, right, that because this is a pure function that has no side effects, we can apply it to each element in parallel. On the other hand, if this wasn't a pure function, it had some side effect like mutating some global state, right? Then we couldn't actually apply it in parallel, right? So this is why pure functions are important, right? Because if they have side effects, then these nice properties that we want our operations to have don't follow. Yeah, we need pure functions in order for it to be safe to do these operations in parallel. Okay, but if we can, and we've got infinite parallel hardware, then in principle, this goes from being an order n operation to an order 1 operation. Now we can carry out reductions as well, like folds, where we apply some operation that reduces our collection to a single value. So that's just reducing with a plus operation. So that one's easy. Can they be parallelized? Well, in general, not necessarily, but very often they can. And that's where the idea of a monad comes in really handy. So a monad in this context, at least, is just a set with a binary relation that's closed and associative, right? And it's really that associativity that allows you to reduce in parallel. Okay, so as soon as we have that associativity, we can basically do tree reduction, right? So we can just start with our values as leaves of the tree and just pair them up pairwise and propagate the values of the tree to get the final sum. And that will work as long as our operation is associative, but it wouldn't work if it wasn't. Okay, so if our operation is associative, again, on infinite parallel hardware, we could go from order n to order log n. Okay, so map reduce, which pretty much everyone has heard of, is just this pattern, right? You map your data in your collection, your data structure, and then you reduce it with some associative operation, and that gives you your value. And lots of interesting computations can be expressed that way. So Apache Spark is a library and framework for doing this at sort of big scale, big data scale, real big data scale, right? So where your data is potentially terabytes big, distributed across a big cluster, and you want to do these kinds of computations. Well, you can do these kinds of computations using Spark. But essentially, all you've got is that same structure we've just talked about. You've got a collection of things. You can do operations on it, like mapping with a pure function, and you can do reductions with associative operations. And there are all kinds of things you can accomplish with that kind of basic computational model. Now, there's a little bit more to it than that, but fundamentally, you've just got this lazy distributed collection supporting the usual sorts of methods you would expect to have on data structures that you use. And so you can use it exactly the same way as you would use other things, and you can build algorithms using it. And the code you write, so for example, log likelihood evaluations, right? You can evaluate across terabytes of observations, right? Just by using this model. And so you can use that as part of your MCMC sampler if you want to. That's totally fine. And the code looks pretty much exactly the same, whether or not this is like a little data set, a little toy data set running on your laptop, or whether it's terabytes of data running on a big distributed cluster in the cloud, because all of the details of the distribution, the parallelization, the synchronization, the communication, it's all taken care of for you via the framework, okay? And the reason that's possible is because you're working in this functional style. So another thing that's had quite a lot of buzz in the machine learning community recently is this library called JAX. Okay, so JAX is a Python library that embeds a DSL for auto diff and JIT compiling array operations. And the idea is that it can allow you to run algorithms that would otherwise run very slowly in Python very quickly, either on a single CPU or on multiple CPUs, or potentially also on GPUs as well. Okay, so it's a way of taking kind of slow Python code and making it run super fast. Okay, and it's very good at this. It really is impressively good at this. And in particular, it's very good for sampling, much better than the other sort of machine learning frameworks for doing sampling, like MCMC. Yeah, so in particular, yeah, it mentions here, it's not unheard of, to get 100 times speed up relative to kind of regular Python code when you just modify it slightly to use JAX, okay, rather than just regular NumPy. So why am I talking about this? Well, I'm talking about it because actually what JAX is, it's not Python, right? It's a pure functional array language that's embedded in Python, okay? And actually a lot of the confusion around JAX comes from the fact that people don't fully appreciate the fact that it really isn't Python at all. It really is a pure functional array language embedded in Python. And so this is why it works fundamentally. It works because it's a pure functional array language. And I think it's really interesting to compare it with Spark, right? Because Spark It's like a completely different thing. So what JAX is doing is getting small to medium-sized problems to run insanely fast on a regular computer. Whereas what Spark is about is analyzing terabytes of data on big clusters in the cloud, typically. Okay, so completely different aspects of scalability, right? They're both scalability, right? But they're completely different aspects of scalability. And yet the computational model is more or less identical. I mean, not absolutely identical, but it's very, very similar to the computational model. In both cases, the idea is that in order to have your computations automatically analyzed and parallelized, and well, JAX's case, auto-diffed, etc., you express your algorithms in terms of lazy transformations of immutable data structures using pure functions, right? That's the Spark model, and it's the JAX model as well. It's almost identical in the sense that if you knew JAX, you'd find it very easy to learn Spark. If you knew Spark, you'd find it very easy to learn JAX. If you know any functional language, you find it very easy to learn either. Conversely, I suspect that if you just had a background in Python and you have no background in functional programming at all, you probably find JAX a little bit confusing at first and probably find it has quite a steep learning curve. But it's just the way we express algorithms in functional languages. Okay, so they've both stumbled on essentially the same computational model, and it's because it allows the compiler, the library, the framework to analyze your code and process it, and that could be JIT compiling it, it could be auto-diffing it, it could be parallelizing it, right? It could be lots of things, but to analyze your code, knowing which bits can safely be done in parallel, which bits can be auto-diffed, etc., in a way that just wouldn't be possible with regular imperative code. Okay, yeah, so that's what I'm saying here, that by expressing in this functional style, right, we can do lots of optimizations automatically, right? So you can analyze the code, you can optimize it, you can compile it, you can parallelize it, you can distribute it, you can differentiate it, you can push it to the GPU, etc. And all of these things don't have to be done by you, the programmer. They can all be done by the library or the compiler or the framework or whatever, right? Because of all the guarantees you get by using kind of principled operations using pure functions on data structures and other notions that have sort of mathematical principles underpinning them. Okay, and it'd be very, very difficult to do this kind of thing, at least to the same extent, using regular imperative code, because once you start, mutating things, having side effects, it's very difficult to do these kinds of analysis and optimizations in the way you can on pure functional code. Okay, so just coming back to JAX again a little bit. So one thing you can do with JAX is write log posteriors using JAX, okay? What do you do with those log posteriors? Well, once you've got them, you might want to sample them. I certainly would want to sample them. So there's a nice library called BlackJAX that will do this. So you just feed in your log posterior, say which kind of MCMC algorithm you want, and you get back a kernel for doing that sampling, and it works super well. But I'm not really a Python person, but my kind of perception as an outsider is that the momentum, especially in the sort of machine learning Bayesian community, is that the momentum is moving very much towards JAX from other backend frameworks. So for example, the original Pyro probabilistic programming language uses PyTorch, and that still exists. But there's a very popular fork of it called NumPyro that uses JAX for its backend and has significant performance improvements. And my impression is that is kind of taking over from the original Pyro. Similar story with PyMC, again, another very popular probabilistic programming language for Python. There was a plan to use TensorFlow for a backend, but that wasn't a good idea. And so now the PyMC3 is being gradually modified to use JAX as its backend. It did use Theano. And I believe it works now. I've not actually tried it, but I believe you can use it now as an experimental feature. Okay, so my impression is very much that within the Python ecosystem, kind of JAX is coming to dominate on the back end for machine learning computations, which is kind of interesting because it's this kind of pure functional language. So that's kind of interesting. Is JAX kind of the last word on this? Well, no, I don't think so. There are some nice things about JAX. I think it is a nice computational model. It has some good features, but embedding this nice pure functional language in a dynamic interpreted imperative language like Python, well, it has a number of limitations. I rewrote that bullet point several times so as not to massively offend lots of people. But there are all kinds of problems with taking a nice pure functional language and trying to embed it in a dynamic interpreted language. In particular, like debugging, it's horrible, right? Because you just don't have any types. So the only way you can find out if your types line up is by seeing everything just crashes and burns horribly at runtime. Right? It's just it's a nightmare, and it's not the fault of the JAX people, right? There's nothing wrong with JAX. It's just if you embed it in Python, that kind of goes with the territory. So, and I know this issue from Spark, right? So Spark is a Scala library, but you may know that there's an interface to Spark from Python called PySpark, and in principle you can write applications in PySpark, but more or less nobody writes non-trivial Spark applications in PySpark, right? They write them in Scala. They might then call them from PySpark, but they write them in Scala for good reason, because you really want a kind of serious programming language for writing serious applications. So this kind of makes you wonder, well, okay, so JAX had some good ideas, but how do we take them and use them not in Python, for example? DEX is one thing that it seems to be coming out of Google research. So Google, kind of the people behind JAX as well. But DEX is just an experimental project, and it's a standalone DSL, so it's not embedded in anything, but it's written in Haskell, and it's a very Haskell-like language. So I mean, maybe it could be embedded in Haskell, and maybe there would be some advantages of doing that. I don't have anything deep and profound to say about DEX particularly, other than it looks very interesting. It's definitely worth looking at, worth playing with, and worth thinking about. Just off the top of my head, there are some things that I like about it and think look really good, and there are other things that maybe don't like so much, but that's okay. This is going to be an ongoing story for decades, I suspect, while we kind of figure out what really are the best ways to solve these scalability problems. Okay, so well, I'm overrunning as usual. So I thought it might be nice, given that there are all these different languages, libraries and frameworks, etc., just to kind of have a bunch of scripts just to analyze a model, and just to show how you can fit exactly the same model, do exactly the same MCMC in a bunch of different libraries and languages and frameworks. So I have done that actually. So the URL is at the top there, so you can go and have a look at that. It's got RJAG, Stan, Python with NumPy, Python with JAX, BlackJack, Scala, Spark, etc. And you can just, I could go through it all in detail and give you lots of benchmarks and things, but that's kind of boring and not really relevant to this talk. But just as a kind of few take-home messages, this JAX really is quite impressive. So for this Bayesian logistic regression model applied to Nicolas' favorite data set, the Pima Indians data set, just taking your NumPy code, just fiddling with it a little bit, changing a few MP dots to JMP dots, writing JIT in a couple of places and threading the random number generator through, you can get it to run 100 times faster, right, than a regular Python version of the code. So that's quite impressive, right? It's not that impressive that you can get something to run 100 times faster than Python, right? If a expert C++ research software engineer spent a month doing it, you'd not be at all surprised if they could get it to go 100 times faster. But the fact that you can just take your NumPy code and just fiddle with a few lines of code and get it to run 100 times faster, I do think is quite impressive. So if you are in this situation where you've got a relatively simple, small to medium-sized problem, and really the only thing you care about is speed, then it seems like at the moment the way to go is somehow express your log posterior in JAX and then probably sample it with BlackJax. But as I say, And the fact that it's embedded in Python does come with some issues.
So,
Okay.
Darren, we have just a question from Lorenzo Paccardi. So you said that JAX has problems because of Python does not have fixed types, but I think there are ways to impose types on function variables in Python, such as a library called typeguard. Is that enough to avoid the issues you mentioned? Thank you.
Yes. So, I mean, that is, so like I said, there's a general swing away from dynamically typed languages, and how that is manifesting itself, or at least one way it's manifesting itself, is that all of these dynamically typed languages are trying to retroactively bolt type systems on top, right? So for example, in JavaScript, there's TypeScript, which is actually very popular. And in Python, there are actually a couple of different attempts at adding types to the language, but this kind of retroactive bolting types on optionally if you feel like it, it's never going to be ideal, and the tooling around it is never really going to work, right? So in a proper language, right, you would never discover at runtime that your types didn't line up. The very worst case scenario, you'd know at compile time, but actually you'd never even get as far as compiling it, because while you were writing your code in your editor would tell you that the types didn't line up, and they tell you exactly the way in which they didn't line up and what you needed to fix in order to make them line up. And so you'd never even get as far as compiling your code, right? So it's just a very different way of working and writing code in these languages that are really designed to be statically typed from the start. And so, yeah, I mean, I think these attempts to add type systems to dynamic languages are kind of interesting, but I'm not sure they're ever going to bring the value that you get by working with a language that is strictly statically typed, from the start. Yeah. Okay, but anyway, good question. Right. So yeah, so as I said, you can have a play with this code at some point. When I finish messing about with it, I'll write it up as a blog post or something. But in some ways, it's a little bit tangential to the bigger picture that I'm trying to get at with this talk. That taking a very simple model like logistic regression and a little data set and getting it to run as fast as possible, right? That's one kind of scalability, but it's not really the kind of scalability that I'm most interested in, right? I'm interested in building big complicated models from simpler components, working with big complicated data sets. So not even necessarily big data sets as in tall data sets, but big data sets as in data sets with lots of structure that makes them not a simple tall thin data set. Yeah. So how do you build big complicated models for big complicated data sets? And not just how do you do it, but how do you do it in a sensible way where you can be reasonably sure that your model is correct? And how can you do it in a way that your inferential algorithms naturally scale along with the complexity of your models, right? To me, that's a much more interesting problem. And so I want to kind of step back and think about what it is, where that scalability comes from, where that compositionality comes from, right? So the argument I'm making is that it's really compositionality that gives you the scalability, and compositionality takes us back to category theory again. So I don't have time to go into lots of details here, and probably this isn't the right time to kind of learn about category theory anyway, but I just want to give some kind of insight into where the connection is between category theory and functional programming and kind of scalable computation. If I can just kind of draw those connections, you can kind of fill in the details later. So a category is basically just objects and arrows. Okay, and the arrows go between pairs of objects. So if you think kind of a graph to start with, a directed graph, that's not a bad first picture, but there's much more structure than there is to a directed graph, because these arrows are closed under composition, right? So if there's an arrow from X to Y and an arrow from Y to Z, okay, then there has to be an arrow from X to Z, and that arrow is called the composition. And this composition has to be associative in the sense that there has to be a notion of equality between the arrows that makes that associativity property correct. Okay, so this is the sense in which category theory is the mathematics of associative composition, right? Because that is basically the definition of the category, and then everything else follows from there. So if you think functions, you're doing fine, right? We know that functions, if you've got a function from x to y and a function from y to z, you can have a function from x to z, which is the composition of the two, and we know that function composition is associative, right? So that's a good model, and actually for functional programming languages, that's actually pretty much the right model to have in your head. So we've talked about collections and mapping collections. Well, the category theory idea of that is the so-called functor. Okay, so a functor in category theory is just a mapping from one category to another. It sends objects in one category to objects in the other. It sends arrows in one category to arrows in the other in the obvious way, so that if you know, x goes to f of x and y goes to f of y, then an arrow that goes between x and y has to go from f of x to f of y, and it has to have a naturality property as well. Actually, no, in this case, it has to satisfy the functor laws. Okay, and the crucial one I want to talk about is this one that I'm kind of highlighting now, which says that if you map f composed with g, okay, that has to be the same as the composition of capital F of f composed with capital F of g. Okay, and this is actually called the map fusion law for reasons that I actually be more obvious on the next slide. But the point is, there are just consistency requirements that you need in order for any of this to really make sense and not to lead to kind of bad contradictions. And category theory is full of these restrictions and laws that are totally natural, right? But by knowing them, you know that there are things that you can do safely, right? You know that there are operations you can do safely. So just relating that back to something really concrete, if we've got one of these Spark RDDs, just a collection of things of type T, okay, and you've got a couple of functions, okay, you've got one from T to U and another from U to V, and maybe you've also got a binary operation which reduces your collection, so you can use to reduce down to a value. You could write something like this in Spark. You could say, I want to take my RDD, I want to map it with F, then I want to map it with G, and then I want to reduce it to a single value using my operation op. Okay, and that will give us a value of type V. And on Spark, that will all be computed in parallel, and the reduction will be done by tree reduction, and it'll all be nice. Okay, but actually what that functor law said was that if you map a container with F, okay, you'll get some intermediary container, then you map it with G, you'll get a new container, and then you reduce it, you'll get a value. Okay, if instead you map with the composition of G and F, you'll just get one container that you then reduce. So you've removed an intermediary collection or intermediary container by fusing those two map operations, right? So that's why it's called map fusion. Okay, and so obviously that's an optimization you can apply to your code, right? But because of the functor law, okay, you know that as long as these functions here are pure, right, mapping with F and then mapping with G is exactly equivalent to mapping with a composition of F and G. And so this will still lead to correct code, right? And so this is an example of an optimization that Spark will perform for you. So if you write the thing on the top in Spark, actually it will rewrite it to the thing underneath and actually just do the optimized version, okay? Because that's an optimization. It knows that it can perform safely, because it knows that you've got a functor and that you've mapped with two pure functions. And so it knows it can use the map fusion law in order to optimize your code, right? And it knows it can do that safely, right? So this is the advantage of using these kind of concepts, these data structures with kind of mathematical principles associated with them, because you know that these are optimizations you are allowed to do and you can do safely without changing the correctness of your code. And again, that's just not something you can do. If these two functions had side effects, you couldn't compose them, right? You couldn't compose them and be sure that the result would be the same, right? You can only do this because, well, because this is a functor, but that's kind of trivial. But because these functions that you're mapping with are pure functions that don't have side effects, right? Otherwise, you couldn't be sure that it would be the same. Okay, so then there's the notion of a natural transformation. So category theory gets pretty abstract pretty quickly. That's just like changing a container type. So you know that in lots of languages, there's a difference between maybe arrays and vectors, and certainly between arrays and lists. But there's an obvious way to change an array into a list and an array into a vector, right? You know how that works. And there is a way to do it that is natural. Okay, but what does naturality really mean from a mathematical point of view? Well, from a mathematical point of view, you just view the object or the kind of the type constructor as a functor, and the neutrality says it doesn't matter if you first map with a function and then change the container type, or first change the container type and then map with the function, right? The result will be the same, right? That's the neutrality law for natural transformations, okay? And again, that is an optimization that can be applied to your code automatically, and you know it will be okay, and you know it will be safe, right? Because that is a law that your data structures have to satisfy, right? And it can be tested automatically, etc. But it's just a requirement that your data structures have to satisfy. And knowing that your data structure satisfies them, you can apply these kind of manipulations and optimizations and operations safely, knowing that you're not changing the correctness of your code. Okay, I'm kind of running out of time, so let's just keep going. There are also monads that we'll come back to later. So a monad is just something that you can flatten. Okay, so for example, if you've got a list of lists, okay, so you've got a list whereas the items of the list are also themselves lists, there's an obvious way to flatten that down to a single list of items, okay? And a monad is just a data structure with that property, right, that you can flatten it. Okay, and the monad law says, well, if you actually had a list of lists, there are two ways you could flatten it. You could first of all flatten the inner two and then flatten with the outer, or you could first of all flatten the outer two and then flatten with the inner, and they have to be the same, right? So again, it's a law, it's a consistency requirement, it's therefore an optimization that could be applied to your code, but it's more just, it's an operation you have at your disposal, and that operation, that flattening operation, turns out to be super useful in lots of different contexts. Okay, I'm going to skip over that. So the categorical dual of a monad is a so-called comonad, and that seems even more bizarre and even more abstract, because you then have a duplication operation. So the idea there is you can maybe take a list of things and turn it into a list of lists. Okay, well, of course you could do that, and there are two obvious ways you could do it. But that seems like an odd thing to do. Is it useful? Well, it turns out it is useful, and it's particularly useful in statistical computing because it solves this problem of how to extend a local computation to a global computation, right? So it solves this convolution problem, the kind of problem that exists when you're doing convolutions of images, or when you're doing a Gibbs sampler over a graph and you want to iterate your sampling from full conditionals across the entire graph. Okay, it solves exactly that problem. So it sounds like an incredibly weird abstract thing from category theory, but it tells you a neat, clean, simple way to solve that problem. And because you're using this mathematical structure, you also know its compositionality properties and the laws that it satisfies and the optimizations that can be done, right? Just all for free, okay? So we really get a huge amount by borrowing these ideas and bringing them into our programming. Okay, so the last thing I wanted to talk about was probabilistic programming languages, okay? So far we've been focusing more on the computation rather than how we kind of build and compose models in the first place, right? So the idea of probabilistic programming languages is we're free to describe the generative structure of our processes that we're interested in, how our data arises, and how the data that arises relates to the variables that we're interested in making inference about. And again, we'd like to do that in a compositional and scalable way. And again, those ideas from category theory help us do that, because it turns out that the monad is the perfect abstraction we need for working with random variables in a programming language. Okay, and in particular, we can represent this notion of a random function or a probabilistic function just using a monad. Okay, and we use the fact that we can flatten monads to chain conditional distributions together. Yeah, so if you chain two conditional distributions together, the types don't match up to start with, right? But you can map the first one with the second one. Okay, so you've got two conditional distributions, right? You can map the the first one with the second one. But then you sort of get a distribution over distributions, right? A random variable, okay? But because you can flatten that down to a random variable, and that's just your marginalization operation, right? So the flattening of your probability monad just corresponds to marginalization, right? So you just use this monadic structure and the fact that monads compose really well to build rich probabilistic programming languages basically for free. Now, of course, it's not that you can't build probabilistic programming languages without monads. Of course you can, people do it all the time. Well, we've mentioned a few already, but by doing it in this way, you get the kind of composability that you really want, okay? And in particular, what you often want to do is build and test a model on a subset of your data, say one group, okay? But then you want to extend that model to a more complicated situation where there are multiple groups, right? So ideally, you just want to take that model and use that as a component in the bigger model. Yeah, that's a perfectly natural thing to want to do, the most obvious and natural thing to do in the world. But actually, if you think about it, in most existing probabilistic programming languages, you can't actually do that. If you wanted to do that, you know, I'll not name names, but in your kind of favorite probabilistic programming language, probably you'd have to do that by copying and pasting code, wrapping an extra for loop around it, and then manually hacking in an extra array index every time you kind of refer to anything, right? That's the kind of thing you do if you're taking a small model and embedding it in a bigger model where there was additional structure, right? That's not compositional. That's not what you want to do. You want to be able to take these probabilistic programs as values in your language and compose them together to make bigger models, right? That's what you need. And this monadic structure gives you exactly that capability. Okay, so we can build models scalably this way as well. I'm running out of time, so I'll just gloss over that. Yeah, so we can build our models in a composable and scalable way. And Bayesian graphical models do have quite a natural compositional structure. Bayesian hierarchical models in particular have a natural compositional structure, okay? So we can exploit that. And sort of probabilistic programming languages are sort of an umbrella for thinking about building and working with these kinds of models in code. But as well as kind of building our models in a composable and scalable way, we'd like our inference algorithms to kind of build and compose and scale in a similar way. Yeah, and again, we can think about that, and you know, these are not all solved problems by any means, but basically, in principle, we can do that, and in principle, we can compose inference algorithms together. So the classic example is you compose together an SMC algorithm with a MCMC algorithm and get a particle MCMC algorithm, right? So in principle, we can do that just by layering things together. But really understanding the compositional structure of our models and the inference algorithms that we're using, right? Different kinds of algorithms have different kinds of compositionality. And so, you know, there's lots of work to be done here. These are not solved problems, but I definitely think there is lots of hope for doing this. And so I'm out of time, so I should just wrap up. So the take-home message is, I think that basically all the languages that people currently use for doing Bayesian computation are not very well suited to the task. They're not very compositional and therefore not very scalable. And you know, looking ahead to the future, I think we need to think about using different modern programming languages. And I would argue strongly typed compiled functional programming languages are a good place to start. And I really think this connection with category theory is very valuable and brings in lots of nice ideas for making our algorithms more scalable and compositional. And that, you know, it's a practical thing, right? It's not a mathematical thing at all. I'm no category theory expert at all, but I think there are real practical benefits from bringing these abstractions into our programming. And I really want to emphasize that it's not just about one programming language or, you know, particular syntax that I like or don't like. It's really not about that at all. It's about classes of languages. So like I said, statically typed compiled functional languages with ideally a few extra properties. And the kind of algorithmic approaches I've been talking about. So in the context of statistical computing, things like lazy transformations of immutable data structures with pure functions is a very natural way to express a lot of statistical algorithms in a scalable and compositional way. So I'll finish with just a few references that they're just references that I think are interesting and in some way tangentially related to some of the things that I've been talking about, right? They're not all like absolutely directly related, but I just think they're all interesting papers. And if you want to kind of follow up on this link here, github.com, Darren JW Talks, I've got a link to the slides, a link to that logistic regression repo I talked about, and a few other links if you want to follow up on anything that I've been talking about. That's it. Thanks very much.
Thanks, Darren. Thanks a lot. Are there any questions for Darren? Okay, so we have one. So you can read it, Darren. We have several.
So one of those I was expecting. So let me do the first one first, right? So the first one says ODE and PDE solvers in JAX and Theano in terms of speed. So I'm not an expert in terms of speed, but I know that there are ODE solvers for JAX. Is it Diffrax it's called? I've not used it, but that's where I'd start. My impression is that Theano itself is abandoned, but it's kind of being reborn as a Sarah by the PyMC3 people. So that's worth keeping an eye on. But I don't like have benchmarks or anything. Julia, I don't have a lot to say about really. It's a bit orthogonal to what I was talking about. I think even its most ardent advocates wouldn't argue that it's a compiled strongly typed functional programming language, and therefore, I just don't have a lot to say about it particularly. Pseudo-random number generators. Yeah, now there's a great question. So I'm increasingly coming around to the JAX model. Okay, so if you look at JAX, it uses splittable random numbers. So if you're going to do pure random number generation in a pure functional language, that there's a standard way to do that, and it's using monads, right? So it turns out it's monads again. It's a standard way to thread random numbers through your computations in a pure functional language in a nice, simple, elegant way. But that doesn't parallelize so nicely. And so JAX uses this splittable random number generator, and I think that ultimately that's probably the right approach. And so I now need to think about how that will work with the standard monads, but I haven't actually thought about that yet. Co-monadic implementation of Gibbs sampling on PGM in Scala. Yes, I have a blog post where I describe exactly how to do that. So if you find my blog, you can find co-monads for statistical computing in Scala or something like that, where I walk through how to do that. But in fact, people do this sort of thing in Haskell as well. Like, the game of life isn't so different from Gibbs sampling, and people, that's a standard, Haskell 101. Why would a co-monad be useful kind of exercise? Okay, any questions I haven't answered there?
Can you hear me? I have a question myself. At the very end, you're telling us what would be the best features of probabilistic programming language. Does this language already exist, or is it something to be invented in the future?
Yeah, largely to be invented in the future. There are a few very interesting steps in this direction. The problem is it's the learning curve. So there was a really interesting experiment in this by Stripe, the payments company, online payments company, Stripe, led by a guy called Avi Bryant. They developed a really nice probabilistic programming language called Rainier that was very much in this phase. But in the end, people found it too hard to get their head around monads, and so they actually rewrote the interface to make it look much more like something like PyMC3, which is fine, but it kind of lost some of the kind of elegance and compositionality when they did that. So I think it's still very much an open question how to do that in a nice way that won't kind of terrify people.
Speaking of which, how did you get to category theory? Did you first learn about Scala and then scalable computation, and then you had to understand all these things, or did you start with category theory?
It was a little bit of both, actually. So, like I said, I'm by no means an expert, but it came up in 3 different places that I'm interested in. So, in terms of systems biology modeling, right? People model stochastic Petri nets using category theory, and I'd sort of seen that. And then with functional programming, category theory is big. And then obviously I'm interested in probabilistic programming languages and probabilistic kind of foundations of inference, and category theory and probability monads are used there as well. So there are like these 3 different areas where I saw it being used, and I thought, well, if it's kind of useful in all 3 of these areas, I really ought to try and learn something about it. But I've very much kind of picked it up on the job as I've been going along.
Well, if you have a book or a paper you would recommend to learn more about it, I think people will be interested. But,
the best way to learn about it. Yeah, well, the standard book is the book by Wody, just called Category Theory. I think that's probably the best book to try and read, but I have to say I found it much easier to learn about it in the context of functional programming, that these concepts seem too abstract to me when I just try to read about them in isolation. And also they tend to use examples from mathematics that I don't always understand, right? It's very kind of complicated areas of mathematics that they use for their examples. So it all kind of came to life to me and started making much more sense when I actually saw how these ideas translated into functional programming. So I still think just actually reading a book like Functional Programming in Scala, it's not a proper category theory book, but it gives you enough of the ideas to kind of start and make those connections.
Okay, thanks a lot. I think we have another question, actually.
On a cluster isn't communication. Yeah, so that's absolutely true. So in that that repo I showed you, because it's running on such a small data set, the parallel Scala version that runs on multiple cores runs slightly slower than the serial version, and the Spark version that runs across multiple nodes on a cluster runs massively slower than anything. So yeah, those problems don't go away, right? What functional programming solves is the writing code simply, elegantly, and correctly problem. It doesn't kind of fundamentally kind of change the limitations of distributed computing, right? Obviously, but these things come into their own at different scales, right? So multi-core on a machine, your data set only has to be a few thousand big before that really starts to pay off. But these distributed frameworks like Spark, right, you really need these massive data sets that really have to have multiple machines before you start seeing benefits, right? So I wouldn't recommend using Spark for anything that will run comfortably on your laptop, right? If it'll run comfortably on your laptop, doing it in Spark will only make it slower. But doing it in parallel, on multiple cores or on a GPU may well make it faster, of course.
I think I don't see any other question. Maxime, do you want to ask?
Yeah, I have one question about asynchrony. So basically, are common languages such as JAX or the languages you speak about actually encompass asynchrony? And
sorry, I missed the question there.
So yeah, so you spoke about parallel computation, etc. But what about synchrony and asynchrony? So basically, can you perform asynchronous computations with those languages or?
Yes.
Yeah, I mean.
Yes is the short answer. The long answer is it's more complicated, obviously, to do everything asynchronously. But yeah, absolutely yes. And all of these functional languages have good facilities for doing this. It requires something a little bit more complicated than what I was talking about here, which is basically just parallel collections. But yeah, I mean, and that's what all of these internet companies are doing. So, you probably know that like all of these big websites, or a lot of the big websites that you use every day, they're all running in Scala, and they're doing everything asynchronously, right? And that's why they run at scale, right? Because everything's happening asynchronously. So the short answer is yes, you absolutely can do all of this stuff asynchronously, but it does require a little bit more effort on the programming side, but it's perfectly doable.
Okay, thanks. So I think there is no other question. Okay, so thanks a lot, Darren, for the talk. Very interesting. Thanks a lot, everyone, for attending this talk.
And let's clap the speaker. On behalf of everyone. Thanks a lot, Darren. That was super interesting.
Thank you.